Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, The pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting. Every year, people throw out 4.4 billion pounds of washing machines. That is like 200 Eiffel Towers made of metal and plastic. But what if your old washer could snag you $200 from Samsung or LG, and then come back to life in a totally new way? In this video, we are going to show you how shredders rip steel apart in seconds, magnets snatch out copper, and plastic gets transformed into new gadgets. Why are brands willing to pay for your old junk? And how can a single machine either help save the planet or end up poisoning it? The first 30 seconds will spill a secret that is going to change the way you think about trash forever. You do not want to miss it. Lots of big brands and electronic stores have programs where you can trade in your old stuff, or they will haul away your old appliance for free when you purchase a new one. For instance, in the United States, companies like Whirlpool, LG, and Samsung have programs like this. Over in Europe, they have initiatives under the Waste Electrical and Electronic Equipment Directive. The details can be different depending on the company. Some will just haul away your old appliance, while others might give you a discount toward your new purchase. Whirlpool in the United States, for example, might offer anywhere from $50 to $100 off a new appliance if you're trading in an old washing machine. LG and Samsung sometimes run special promotions where they might offer $100 or even $200 back. Over in Europe, some programs might let you get up to a 10% discount on a new appliance. But more often than not, the discounts are not that big. Most companies really look at this as more of an environmental effort, not just a strategy to pull in customers. In a lot of cities, you will find electronic waste collection centers where people can drop off their old washing machines themselves. These centers often team up with local city governments or private recycling companies. In some countries, like Germany, the United Kingdom, and the United States, there are city-run services that will actually come and pick up bulky electronic appliances. For example, in New York City, you can schedule a free pickup through the city's own program called NYC Safe Disposal. There are also some companies that focus specifically on recycling metals. They might actually buy your old washing machine from you, or at least take it off your hands for free. These companies then send the appliances off to be taken apart, where they pull out all the valuable stuff like metal, electronics, and plastic. First things first, the machines get sorted into different groups. Ones that still work, ones that kind of work, and ones that are completely broken. The machines that still work might get fixed up and resold, but the ones that are too far gone head off to be taken apart. The teardown process starts by taking off the outside panels, the door, and the drum. Things like motors, electronic components, wiring, and pumps are separated out because they can often be reused as parts or melted down for their materials. The different types of metal get sorted separately, like stainless steel, aluminum, and copper. Plastic parts are also gathered up and sent off for recycling. This whole process can be done by hand, or it can happen on special automated lines where machines shred the main body and then use things like magnets and air separators to sort out the different materials. These automated recycling lines for washing machines usually involve several steps, and each step is designed to separate out specific types of materials. First, the washing machines are loaded onto a conveyor belt that feeds them into powerful rotating shredders. The blades on these shredders are strong enough to rip through the metal and plastic bodies, breaking them down into pieces roughly 1 to 4 inches across. Once everything is shredded up, the mix of materials moves past magnetic separators. These magnets grab onto any metals that are attracted to magnets, like steel and cast iron, pulling them away from all the other stuff. Next up is something called an eddy current separator. It uses a different kind of magnetic field to actually push away the non-ferrous metals, things like aluminum and copper. Plastics and other lightweight materials get separated out using air separators. Basically, strong blasts of air blow the lighter bits, like plastic flakes, upwards and into collection bins, while the heavier stuff stays put on the conveyor belt. Toward the end of the sorting line, whatever materials are left might go through optical scanners. These scanners can analyze what the pieces are made of and sort them even further, sending them to the right place for more processing or final disposal. So, after all this sorting with air separators and optical scanners, the different materials head off to their own separate processing lines. This is where the plastic, metal, glass, and anything else gets processed so it can be reused or recycled properly. The leftover metal pieces, like the steel parts, are shipped off to metal processing plants. There, they get melted down and eventually used to make brand new products. Remember those magnetic separators? They are super effective at pulling out iron and steel, which then get sent off to be melted down. The plastic parts get shredded into smaller pieces and then usually compressed into dense bales or blocks. These bales can then be shipped to specialized factories where they will be used to make new plastic items, or they might become part of the raw material mix for new appliances or other tech gadgets. If the washing machine had any glass parts, maybe in the door window, that glass gets cleaned really well to remove any gunk, and then it can be melted down to make new glass products. Any leftover materials that cannot really be recycled, maybe certain kinds of rubber or complex mixtures of stuff, usually end up getting sent for final disposal, often meaning they go to specially designed landfills. These kinds of sorting and recycling setups drastically cut down on the amount of waste that just gets dumped in landfills. Plus, they help get valuable raw materials back into the economy so they can be used again. Sometimes, especially for really tricky materials, they have to use more advanced techniques, like thermal decomposition, which uses heat or special chemical treatments. These methods come into play for stuff that is hard to separate just by shredding and sorting mechanically, or for materials that need extra processing to make sure they do not cause pollution or release harmful substances. Good examples are certain plastic components that have other materials embedded in them, like plastic with metal pieces fused inside or attached rubber seals. Materials like these often cannot be sorted easily using the standard methods, so they need special treatment to break them down and separate the different parts. Rubber parts, particularly those made with complex chemical additives, are often tough to recycle effectively because of their complicated structure. For materials like that, processes like thermal decomposition or other chemical methods might be used. The goal is to basically unzip them into simpler building blocks that can potentially be reused or at least disposed of more safely. In situations where the appliance contains hazardous stuff, think mercury in old switches, or maybe some types of batteries or old lighting components, those materials absolutely have to be handled with special procedures. This might involve a chemical process designed to neutralize the dangerous parts, or maybe one that locks them up safely so they can be disposed of without causing harm. Materials like polyurethane or polyester, which you often find used as insulation around wires or in various other parts inside appliances, might also be treated with thermal decomposition. This helps break them down into simpler substances that could potentially be recycled. And then you have situations where washing machines or other electronics contain complex composite materials. Stuff made of several layers of different materials bonded together, like plastic fused with metal layers or reinforced with fibers. These often require very specialized processing to carefully separate the layers so that each material can hopefully be recycled on its own. Overall, the reason for using all these different technologies is to make the whole disposal process as efficient as possible and to minimize the harm done to the environment. Because if these materials are not handled the right way, you could end up with pollution or dangerous chemicals leaking out into the ground or water. Did you know that your old air conditioner could poison the soil, wreck the ozone layer, and even cost you thousands of dollars in fines? Every single year, Americans throw out millions of air conditioners, and each one is a ticking time bomb of toxic chemicals, heavy metals, and dangerous gases. In this video, I'm going to show you how they actually get recycled. Freon, copper, mercury, nothing gets spared. And trust me, this affects all of us. So first things first, why should anyone bother recycling an air conditioner the right way? To answer that, let's break down what's actually inside one of these machines. Air conditioners contain refrigerants. These are chemicals that can do serious damage to the atmosphere. Older units use ones that destroy the ozone layer. Newer ones, they may not harm the ozone, but they still contribute to global warming. The internal boards and compressors are loaded with toxic stuff like lead, mercury, and cadmium. If you just dump an old AC in a landfill, all that junk can leak out into the ground and water. Now, compressors also contain valuable metals like copper, aluminum, and steel. Those can be reused, cutting down the need to mine more raw materials. But here's the kicker. If you try to tear one of these apart without the right safety measures, those toxic materials can leak out, fast. That's why so many countries, including the United States, have strict environmental laws banning improper disposal. And yeah, in some cases, those fines are no joke. In the United States, old air conditioner disposal is regulated on a federal level by the Environmental Protection Agency, plus individual state rules on top of that. Now, we've already touched on how long these machines usually last. So let's dive deeper. Window and portable units typically last from 8 to 10 years. Split systems? They give you a few more. And those big centralized setups, yeah, the ones we mentioned earlier, they'll run for about 15 to 20 years. Keeping filters clean, topping off refrigerants, and doing regular checkups can stretch that lifespan. But in hot areas where ACs run all summer long, they tend to wear out faster. Once your system hits the end of its life, it loses efficiency. Your power bill goes up and repairs become a money pit. That's why most people end up replacing them, which means more units headed for recycling. There are several ways to recycle air conditioners in the US. A bunch of utility companies run take-back programs for old ACs. Some even offer cash, anywhere from $25 to $100, just for handing your unit over. All you gotta do is apply, and a technician comes out to pick it up and handle it properly. Big chains like Best Buy, Home Depot, and Lowe's will take your old AC for recycling too. Some states have dedicated drop-off sites for electronic waste where you can bring in your unit for free or a small fee. In many cities, there are special bulky item collection days. And some towns offer curbside pickup of old appliances, sometimes even for free if you book ahead. Even charities like Habitat for Humanity Restore take working ACs to resell or use in community programs. And a lot of stores have trade-in deals, where you bring your old one in and get a discount on a new model. When we're talking about centralized systems though, you can't just yank one out yourself. You need to call a licensed tech. They'll recover the leftover refrigerant using special equipment, then ship the whole system off for proper disposal. In many states, improper disposal can mean fines, from $100 to $500 on average. But in some cases, it can climb into the thousands. Bottom line, either take your unit to a recycling facility or use one of those special programs. That's the smart move. Once the AC arrives at the facility, the first step is a professional teardown to safely remove hazardous materials and prep everything for recycling. Removing Freon is a whole process that needs special tools designed to safely extract it from the system. The technician hooks up a refrigerant recovery machine to the AC's tubing system. This device uses vacuum pumps and pressure gauges to control the flow. The system gets opened through service valves, giving access to the Freon lines. The vacuum pump slowly pulls the refrigerant out and transfers it into a sealed recovery cylinder. The tech keeps an eye on the gauges to monitor pressure and make sure every last drop is extracted. Depending on the unit size and how much refrigerant is inside, this process can take anywhere from a few minutes to half an hour. During this step, the workers are fully suited up because contact with refrigerants can be harmful. The equipment's built to prevent any leaks. Everything happens in a sealed environment. Once the Freon is removed, it's stored in that sealed tank and later handed off to certified hazardous waste recyclers. With the refrigerant safely gone, the unit moves on to the disassembly phase, which is crucial for proper recycling. The techs set up special workstations at the facility. Before disassembly starts, they review the paperwork and lay out a plan, so they know exactly which parts to pull and how to sort them. The AC gets broken down into its core parts: the outer casing, compressor, heat exchanger, fan, electronics, piping, and smaller components. A typical unit has around 20 to 30 different pieces. The compressor alone might weigh between 30 and 50 pounds. Radiators, anywhere from 20 to 40 pounds each. They use both hand tools and machines, like hydraulic lifts and electric grinders, to cut or unbolt the big metal parts. This step takes about 30 minutes to 2 hours per unit, depending on size and complexity. Once everything's apart, the pieces are sorted by material: metal, plastic, and electronics. Around 90% of the metal in an old AC can be recycled. Metal gets cleaned of paint and grease, then sent for smelting and reuse. Plastics go to specialized recycling plants. Electronics that contain dangerous stuff, like lead and cadmium, are sent to e-waste recycling centers. On average, just one unit can provide 5 to 15 pounds of recyclable metal. That's a big deal when it comes to saving raw resources. Many recycling centers handle tens of thousands of air conditioners every year. That keeps a massive amount of toxic waste out of landfills. After the unit's fully disassembled, the next key step is sorting and prepping the materials for reuse. This process helps maximize resource recovery and shrink the environmental impact. After the initial cleaning, materials are sorted by quality standards. Metals get split into categories: aluminum alloys, steel, and copper. For example, copper wiring is often separated because its market value sits around $4 to $5 per pound. Plastic waste is grouped by type. The bundles for recycling usually weigh between 5 and 20 pounds. Electronic components are sorted by type: motherboards, capacitors, batteries. So recyclers know which ones need special handling, especially those containing rare metals. After sorting, all materials are packed up for transport. Metal parts go into containers headed for smelters. A single container can hold anywhere from 500 to 1,000 pounds of metal. Plastic granules are bagged or boxed up, usually in 50 to 100 pound batches, ideal for manufacturing. Electronics are shipped to specialized facilities where they get broken down even further. Thanks to this whole process, a single air conditioner can yield a surprising amount of reusable material. Recycling and disposing of A to C the right way also saves energy. Smelting recycled metal takes about 60% less energy than making new metal from raw ore. And today, some companies are already rolling out tech to automate disassembly and sorting, making the whole system more efficient and less dependent on human labor. Have you ever seen a ship that does not touch the water? Now, imagine that such a vessel not only exists, but can also carry tens of tons of cargo and accelerate up to 250 miles per hour. Meet the Hovercraft landing craft, a unique combat vehicle that glides above water, land, sand, and even ice. Its engines are just like those in fighter jets, and its maneuverability lets it drift on waves. But how much does this technology cost? How do they build it? And why are even seagulls afraid of these machines? Let's find out. The idea of using an air cushion came from the British engineer Christopher Cockerell in the 1950s. He experimented with airflows using tin cans and a hairdryer, ultimately creating the concept of a vehicle that could glide over any surface. In 1959, the world's first real hovercraft was launched. Later, this technology found its way into military use, specifically in LCAC-type landing crafts developed in the United States during the 1970s. So, Cockerell invented it, but the military refined the idea into its modern form. Let's move forward. Or maybe sail ahead. Manufacturing hovercraft landing crafts involves several stages. Initially, design bureaus create drawings and digital models of the craft. The design process depends on whether it's a new project or an upgrade of an existing one. Creating a completely new hovercraft takes from 6 to 12 years. Imagine that. Preliminary design and concept stages last from 1 to 3 years. Developing drawings and digital models adds another 2 to 5 years. Building and testing the prototype takes an additional 3 to 5 years. Finally, we get a ready-to-use craft. If we're talking about upgrading an existing design, the process takes half the time. Analysis and adaptation of drawings take from half a year to 1 year. Updating digital models takes only 1 or 2 years. Building and testing the updated version takes 2 to 3 years. The newest American hovercraft, called the Ship-to-Shore Connector, replacing the LCAC, began development in the 2000s. The first test models were ready in 2012 and 2014, but full-scale production started only in the 2020s. The process is lengthy because these crafts must be reliable, fast, and suitable for challenging operational conditions. After drawings and digital models are developed, suppliers of materials and components are selected. The military announces tenders, where companies compete for contracts. Manufacturers must pass certification and prove their materials withstand extreme conditions. Some components are produced exclusively domestically for national security. Thus, the process is complex but critically important. If even one component fails, the entire mission can be jeopardized. The craft's frame is assembled at shipbuilding yards. These massive industrial complexes are usually located on coastlines or near large rivers. They cover areas from dozens to hundreds of acres, since multiple vessels must be built simultaneously, with space for storing materials and heavy equipment. There are huge covered or open areas where ship hulls are assembled. These areas can be from 500 to 1,500 feet long to accommodate large structures. In metalworking workshops, aluminum alloys for the LCAC hull are cut, welded, and shaped using robotic machines and laser cutting. Shipyards also include dry dock basins, enormous artificial pools, where finished crafts are tested before launching. Massive gantry cranes with lifting capacities from 100 to 1,100 tons move large sections of hovercrafts. Additionally, there are areas for installing gas turbine engines, radar, and navigation systems, as well as logistics yards, where incoming materials and components from suppliers are stored. One of the largest such shipyards in the United States has been building military vessels for more than 100 years. The frame assembly of a hovercraft landing craft is constructed mainly from aluminum alloys, using welding and assembly methods different from traditional shipbuilding. Aluminum sheets and profiles are supplied as ready-made blanks. Robotic machines cut out parts according to computer-generated drawings. Sections for the future frame are prepared in special workshops. The LCAC structure is not assembled entirely at once, but built from large modules. Each module, for example, the bow, stern, and side sections, is assembled separately. Rivets and aluminum welding ensure durability. The frame consists of a keel beam running the length of the craft and transverse ribs providing rigidity. Aluminum rivets and specialized adhesive mixtures are used to connect sections, reducing weight. Large modules are lifted by powerful cranes and connected precisely using laser positioning to avoid errors. At the brightly illuminated shipyard, a giant module of the future craft rises into the air. A heavy gantry crane, weighing hundreds of tons, slowly lifts the aluminum section, gleaming in the sun like the shell of a marine predator. Metal cables are stretched tight like strings, while workers in protective helmets and vests carefully monitor every movement. The enormous part floats mid-air, gently swaying in the breeze. A crane operator, sitting high above the yard, maneuvers this colossus with extreme precision. Engineers below signal instructions, guiding the module to its exact position. When the section slowly settles into place, there's a dull metallic thud. Thousands of pounds of aluminum collide with the frame. Immediately, fastening begins. Workers tighten bolts, welding machines ignite with bright blue flames, and sparks scatter from beneath electrodes. The air fills with the scent of hot metal as the craft gradually takes shape, becoming a formidable combat machine. Engineers inspect structural integrity and tightness. Attachment points for the hovercraft skirt are installed on the frame. This system must be completely airtight to maintain LCAC stability during movement. The completed frame undergoes load and vibration tests. After passing successfully, engines, propellers, and electronics are installed. Now begins one of the most critical stages. The shipyard hums with crane motors, gently transporting massive gas turbine engines, the heart of the future craft. Workers dressed in protective suits and masks precisely position them in compartments, where every millimeter counts. Simultaneously, technicians attach enormous propellers, blades made from robust composite materials, which will later propel air with thousands of horsepower. When blades rotate for the first time, air waves ripple through the air, causing fabric on work uniforms to tremble. Inside, engineers connect cables, sensors, and onboard computers, carefully inspecting every chip, screen, and controller, as navigation, communication, and automated control depend on these systems. Once everything is ready, the moment of truth arrives. Pressing the first launch button, the massive frame shudders, turbines roar to life, and the first stream of hot air bursts from exhaust channels. The LCAC is ready for its first water test. A single modern LCAC costs from $50 to $75 million, depending on modifications. Operating costs are high due to gas turbine engines and demanding maintenance. Maintenance can occur at shipyards or specialized bases. Gas turbine engines require frequent service due to limited lifespans and costly repairs. The Hovercraft skirt wears from contact with water, sand, and stones. Propellers and air systems require repairs as they operate continuously at high speeds. The United States is the leading producer of the new ship-to-shore connector crafts, replacing older LCACs. Great Britain builds similar crafts for civilian and military markets. Who uses them, you might ask? The United States Navy is the largest operator, possessing about 70 LCACs and acquiring new models. Japan uses LCACs for defense and humanitarian missions. Potential customers include NATO countries and nations expanding amphibious forces, like India and South Korea. Currently, LCACs are being upgraded to SSC, quieter, faster, and more efficient crafts. Demand is rising due to threats in the Pacific region and the need for rapid troop transport. Additionally, LCACs can drift. With the air cushion, they lack typical friction with water or land, allowing them to slide sideways, sharply change direction, and even pivot almost in place, making them exceptionally agile but challenging to control. LCACs use the same gas turbine engines as military aircraft, specifically the General Electric LM2500. Similar engines power FA-18 Hornet fighters. Essentially, LCACs are aircraft that never leave the surface. Unlike conventional ships, they can move onto shore, cross sandy dunes, swamps, and even ice, providing advantages for landing troops in difficult locations. However, LCACs are among the loudest vessels in naval forces. Their noise can be heard hundreds of feet away, making them unsuitable for stealth missions. During operation, LCACs create powerful vortices, capable of literally blowing away seagulls and other marine birds, often making it impossible for them to remain airborne. Every single year, the world's oceans are left with hundreds of gigantic liners that used to be floating cities. Imagine this. Only one specialized shipyard in the country of India dismantles over 400 ships per year, and the utilization of just one cruise liner can yield up to about 44,000 short tons of steel. How does a vessel that once cost billions of dollars turn into a heap of scrap metal? Who makes money on this process? And why do the majority of ships finish their journey in Southern Asia? Let us examine this process from the very first blueprint all the way to the very last cutting of the hull. Private yachts are produced all over the world, including in the United Kingdom, the Netherlands, Italy, and Turkey. But the major cruise liner production hubs are located in France, Germany, Italy, and Finland, where industry giants such as Chantier de l'Atlantique, Meyerwerft, and Fincantieri operate. Everything begins with the creation of a project, during which engineers and designers develop the overall structure, choose materials, and determine the technical specifications of the vessel. The design phase can last anywhere from 6 months to 5 years. Once it is approved, the shipyard begins manufacturing the main metal sections of the hull, which are later joined together in a massive dry dock or a specialized construction hangar. Construction starts with the production of large steel or aluminum sections that will form the hull. First, enormous sheets of metal are cut using laser or plasma cutting, and then they are joined by welding to create separate blocks. Each block can weigh anywhere from about 55 short tons to about 330 short tons, and their total number may reach into the hundreds, depending on the ship's size. After the welding is completed, the sections are painted with anti-corrosion coating and moved into a massive assembly dock, where the hull begins to take shape. The assembly process involves powerful cranes that lift the blocks and connect them to one another. Once the main structure is finished, the hull is reinforced with internal bulkheads, and initial communications are installed, including piping systems, ventilation ducts, and electrical cables. When the hull is fully assembled, it is launched into the water, and the fitting out of the interior begins. Partitions, electrical grids, heating and ventilation systems, air conditioning, and safety systems are put in place. At this stage, the ship gradually starts to look the way it will when it is completed. First, special soundproofing and thermal insulation materials are applied to the ship's metal hull, because the liner must be not only strong, but also comfortable. Next, metal frameworks are installed to serve as the foundation for the partitions and other structures. These frames are made of lightweight materials, such as aluminum or composite panels, to keep the vessel's overall weight lower. Thanks to modular technology, large sections of cabins and public areas are assembled at separate production facilities and then transported to the liner, where they are rapidly installed. Passenger cabins are usually manufactured as complete blocks, each including walls, flooring, plumbing, and furniture. These blocks are then transported to the ship and placed in their designated spots, after which they are connected to the ship's electrical network and water supply and ventilation systems. Larger liners can have more than 2,000 of these modules, and installing them can take several months. Public areas are much more complex, since each restaurant, theater, or lobby has its own design and intricate architectural solutions. For example, theater stages are equipped with moving platforms, sound systems, and lighting that is integrated into the ceiling. Swimming pools receive water purification systems, and sports courts are fitted with special non-slip surfaces designed to withstand wave movement. During the final stage, furniture, decorative panels, lighting, and finishing touches are installed. High-quality materials are used, ranging from exotic woods and marble to stained glass. Designers pay attention to every single detail in order to create an atmosphere of luxury and comfort. Once construction is complete, all systems undergo meticulous testing, including elevators, ventilation, safety features, and communication lines, so that the liner is fully prepared to welcome passengers. At the same time, powerful engines and control systems are installed on board. The main engines, which are typically diesel or hybrid, are mounted in the engine room before the liner's hull is completely enclosed. Each engine can weigh anywhere from about 22 short tons to about 55 short tons, and there may be between 3 and 6 engines depending on the ship's size. They are delivered to the shipyard dock by specialized cranes, then lowered through the engine room's top hatch and attached to vibration damping mounts that reduce noise and vibration during operation. After the engines have been installed, drive shafts are added to transmit rotational motion to the propellers, or, in the case of electric motors, they are connected to the power supply system. Most modern liners use azipod units, which are powerful electric motors capable of rotating around their own axis, giving the ship excellent maneuverability. All power units are connected to control systems located on the bridge and in the engine room. Once every technical system is in place, the liner is readied for its initial tests. First, static tests are conducted while the ship is still in the dock, checking how the engines function without leaving port. The power units are started up, and the electrical supply, fuel pumps, cooling systems, and emergency mechanisms are tested. Computerized control systems, which manage navigation, automatic speed adjustment, and ship stability, are also checked at this stage. Following these static tests, the liner is launched for sea trials, which last from about 2 weeks to about 6 weeks and include checking speed, maneuverability, and the operation of all systems under real-world conditions. The captain and technical personnel test how the vessel responds to commands, examining braking efficiency and the performance of the stabilization systems. The liner is taken into open waters, where the engines are tested at maximum power. Fuel consumption is measured, and noise and vibration levels in cabins and public areas are evaluated. In the final phase of testing, safety systems are examined by simulating emergency scenarios, testing firefighting systems, lifeboats, evacuation routes, and communication with shore-based services. Only after all tests are successfully completed is the liner formally handed over to the client, and it sets sail on its maiden voyage. But sooner or later, every liner heads out on its last voyage. Since no technology lasts forever, what happens to yachts and other vessels afterward? Are they actually utilized? And if so, how? According to data from the International Maritime Organization, around 1,000 seagoing vessels are utilized each year, of which about 200 are large cruise liners and passenger ships. Most of these vessels are dismantled in South Asian countries such as India, Bangladesh, and Pakistan, where the world's largest ship utilization shipyards are located. For instance, in the city of Alang in India, there is one of the biggest shipyards, which processes over 400 ships per year. First, the ship's owner assesses the condition of the liner and compiles a list of materials that can be recycled, sold, or require specialized disposal. The utilization of a single large cruise liner can produce up to about 44,000 short tons of steel, which, after recycling, is used in construction and other industries. In addition to metals, other materials such as wood, glass, and plastic are removed from the vessels for recycling or safe disposal. During this period, the ship heads to the specialized shipyard that handles the disassembly of ships. The largest of these facilities are located in India, Bangladesh, Turkey, and Pakistan. The liner or yacht makes its way to the site for utilization under its own power, or is towed if its engines are no longer functional. When the vessel arrives at the shipyard, the preparatory work begins. A team of engineers and environmental specialists evaluates the potential risks connected to hazardous substances, including fuel, lubricants, coolants, chemicals, asbestos, and lead. All of these materials must be carefully removed to prevent environmental contamination and to protect the workers' safety. In the first step, any remaining diesel fuel is pumped out of the tanks, which can amount to anywhere between about 10 short tons and about 55 short tons, depending on the size of the vessel. Next, the pipelines, oil filters, and engine cooling systems are cleaned to remove all residual lubricants and chemicals. Specialists also deal with air conditioning and firefighting systems, which might contain harmful gases like freon. After that, the ship is disconnected from all power. The electrical networks are shut down, and the batteries containing toxic substances are removed. In the engine room, the generators are dismantled. They can be resold or used on other ships. During this period, specialists also check for hazardous materials, such as asbestos, which was once used for pipe and wall insulation. Asbestos is carefully taken out, sealed, and delivered to specialized facilities for safe disposal. The next step involves removing all equipment and items that might be reused or sold. Furniture, lighting fixtures, plumbing, doors, decorative panels, carpets, and even kitchen appliances are dismantled from the liner. Many of these items are sold on the secondary market or used on other vessels and in hotels. The following stage is dismantling. First, the ship is secured in a dry dock or pulled onto a specially designated beach, which is common in South Asian countries such as India or Bangladesh. This stabilization is necessary to keep the hull steady during cutting, because losing balance could cause an accident. Next, the upper structures are gradually taken apart, including the top decks, bridge, funnels, and other external components. These sections are typically removed in large pieces using cranes. Workers start dismantling the upper structures and decks, steadily moving down toward the main hull. Metal parts like steel and aluminum are cut into smaller segments, and the separated materials are sorted and prepared for subsequent recycling. For example, steel is melted down to create new products, while non-ferrous metals such as copper and aluminum are put to use in various industries. When the upper structures have been fully removed, the main hull is cut apart. Several methods can be used, depending on the thickness of the steel and where the ship is located. The most widespread method is gas cutting, where specialized torches heat the metal to over 1,500 degrees Celsius, which is about 2,732 degrees Fahrenheit, and then the steel is sliced by a stream of oxygen. For thicker steel sections, which can be up to about 8 inches thick, plasma cutting or hydraulic shears may be used. Cutting of the hull begins from the top and proceeds downward, so that the structure does not collapse under its own weight. Huge steel blocks, weighing anywhere from about 55 short tons to about 110 short tons, are separated and moved to specialized areas, where they are further broken down for recycling. On average, the hull of one large cruise liner can yield from about 33,000 short tons to about 44,000 short tons of steel, which is later reused in construction and shipbuilding. Special attention is paid to cutting the underwater part of the hull, since it is the sturdiest section and contains ballast tanks that might hold residual water. Underwater welding and cutting techniques are employed if part of the hull remains in the water at that stage. In the final phase of dismantling, the last remains of the keel and bottom are cut into fragments, which are loaded onto trucks or barges for transport to metallurgical plants. Utilization of cruise liners and yachts can last from a few months to more than 1 year, depending on the vessel's size and construction. Completing the dismantling process signifies that the ship officially ceases to exist. All materials suitable for reuse are sent for recycling, and everything else that cannot be repurposed is disposed of in accordance with environmental regulations. It is important to note that the utilization process must meet international environmental standards. Organizations such as the International Maritime Organization develop guidelines and standards for the environmentally sound utilization of ships, known as the Hong Kong International Convention for the Safe and Environmentally Sound Recycling of Ships. Imagine a place where the trains of the future are born every single day, a place that brings together innovation, sustainability, and history. The Siemens Mobility Factory in Sacramento is over 2 million square feet of manufacturing space, creating the locomotives that move America. Here, one of the largest 3D printers in the world is installed, and up to 80% of the energy comes from solar panels. Curious about how trains are tested? They are run on specialized tracks to evaluate speed, noise, and stability. This is not just a factory, it is a true innovation lab. The story of this factory began back in 1984, when Siemens decided to invest in the future of rail transport in the United States. But they needed more than just technology. They needed a reliable base, and Sacramento was the perfect choice. What does the capital of California have to do with train manufacturing? Actually, the location choice was very strategic. Sacramento has a long history of railroad infrastructure. As far back as the 19th century, this city was one of the key hubs of the Transcontinental Railroad. In other words, the railway spirit has been alive here for over 150 years. Additionally, the region had access to a large number of skilled workers who could contribute to manufacturing. On top of that, the proximity to ports and other transportation hubs in California ensured smooth logistics. When the factory first opened, it was relatively small. Siemens Mobility was just beginning to build its brand in the United States. Initially, the factory specialized in manufacturing locomotives and trams. However, the company's ambitions were massive. They saw the need for modernizing American rail transport and decided to become part of this revolution. Within just a few years, the factory began scaling up production while implementing cutting-edge technologies. Over time, it started producing trains that you can now see in dozens of American cities. The Siemens Mobility Factory continued to grow. In the 2000s, it began producing modern high-speed trains and electric trains that meet the highest standards of comfort and energy efficiency. One of the key milestones was the expansion of the manufacturing facilities. The factory grew to over 200,000 square meters. This allowed for increased production capacity, the addition of new car manufacturing lines, and even testing grounds. Today, the Siemens factory in Sacramento is one of the most sustainable manufacturing sites in the world. Approximately 80% of its energy comes from on-site solar panels. Water usage is maximized for efficiency, and nearly all material waste is recycled. By the way, this factory produces trains for Amtrak, Brightline, and various urban rail systems, including the Los Angeles Metro and Minneapolis streetcars. The factory emphasizes localization. About 90% of the materials used in train manufacturing are supplied by American companies. This not only reduces logistics costs, but also supports the local economy, enables quicker responses to market needs, and ensures that the products meet client requirements. Siemens Mobility does not stop innovating. They are already working on trains with hydrogen engines and autonomous driving systems. While specific statistics on these projects may be limited due to commercial confidentiality, it is known that the company invests significant resources in research and development in these areas. So, how are trains made? It all starts with large sheets of aluminum and steel, which are cut and formed into components for train cars. And you know what? I was amazed by how organized the process is. Even at the stage where you are just looking at pieces of metal, everything is planned down to the smallest detail. Assembling a single car can take weeks, and an entire train, months. But the result is worth it. When they arrive at the factory, they are immediately distributed into zones based on what will be made from them: walls, floors, roofs, or smaller components. This is not just a pile of metal. It is all sorted and labeled with special codes. This ensures that no piece gets lost and that production does not halt due to confusion. The metal is cut on specialized machines that use lasers or plasma cutting, and there is no room for error. Every piece is cut with millimeter precision. But here is the interesting part. There is almost no waste. Leftover pieces are reused to create smaller components or sent for recycling. This is not just cost-saving, it is sustainable. The metal is used, for instance, to create train car exteriors. These are made of aluminum for a good reason. This material is both lightweight and strong, making it ideal for high-speed trains. I was even told that it is environmentally friendly. Aluminum can be recycled almost infinitely. Impressive, right? Cutting robots and hydraulic presses create parts that undergo further processing. Everything here is ultra-precise. There is no eyeballing it. In the next workshop, the train's frame is welded. Once the car bodies are ready, robots and highly skilled workers step in. I watched as each part was installed one by one, from roofs to floors, from walls to doors. It is like a massive Lego set, but on a scale you can hardly imagine. In this workshop, the car frame is born. Every weld is checked to ensure it can withstand future loads. Imagine sparks, bright lights, and sounds like in a blacksmith shop, but with robots. Workers install windows, doors, seats, electrical systems, ventilation, everything that makes a train comfortable for passengers. Next, the train is painted with weather-resistant paint. And yes, everything here is as eco-friendly as possible. Filters capture harmful substances to prevent environmental damage. But the most fascinating part starts with the details. Did you know that every train car interior is essentially a small universe? Wiring, control systems, air conditioning, seats, everything is installed with meticulous precision. One worker even joked, "Every single screw here is worth its weight in gold." Another thing that amazed me was how many processes are automated. For example, electronics inside the cars are tested using special simulators. It is like a video game where the system checks if all buttons, displays, and even Wi-Fi are working. Now picture this. Before a train hits the tracks, it is tested on a special track. Yes, they literally run it here to measure speed, stability, and even noise levels. Watching this giant accelerate is a whole new level of satisfaction. Here is what makes factories like Siemens Mobility special. Everything works in harmony. On one hand, there are people working with their hands, putting a piece of themselves into every car. On the other hand, there are robots and automated systems making the process faster and more precise. I was even shown one of the largest 3D printers in the world, which prints train parts. Imagine this. Instead of waiting for parts to be delivered from across the globe, the factory can make them right here, right now. It is not only convenient, but also eco-friendly. Less transportation means fewer emissions. For instance, the 3D printer produces mounting nodes, frame elements, and even special ventilation components. Traditionally, these would need to be cast or welded, but here everything is done more precisely, faster, and more efficiently. Fairings, structural components, interior details, spare parts, and prototype versions of parts can all be printed, saving materials and time. Okay, some might ask, what is so special about this? Trains are just trains. But no, each of these modern cars is a step forward in transportation development. More sustainable materials, energy-efficient systems, passenger comfort, all of this impacts not just us, but the future of our planet. Moreover, factories like the one in Sacramento create jobs and introduce new technologies that can later be applied in other industries. It is a place where technology and people come together to create something truly remarkable. Oh, you cannot even imagine how massive this factory is. The Siemens Mobility facility in Sacramento spans approximately 2 million square feet. Picture several football fields connected into one giant structure. It is a city within itself. Workshops, conveyors, rail tracks, repair shops, and even test tracks for finished trains. The factory is divided into several zones, each responsible for a specific stage of production. When I left the factory, I felt like I had visited the future. This is a place where innovation, craftsmanship, and human talent combine. If you ever get a chance to visit something like this, Do not miss it. It is truly impressive and changes how you see the world. So, are you ready to hop on a train next time and think, how was this made? Imagine this, a house printed in just 24 hours. Sounds like science fiction, right? But it's real. Back in 2018, the United States saw its very first 3D printed house. Today, there are hundreds of these homes, and the numbers keep growing. This technology doesn't just build houses. It's redefining architecture with designs that are both stunning and efficient. And the best part? A home like this could cost as little as $10,000. Ready to see how a giant printer turns concrete into cozy living spaces? Let's dive in. The first 3D printed house in the US appeared in 2018. Now, there are hundreds of these homes, and the count is steadily climbing. Let's start with the basics. 3D printing is a technology that creates objects layer by layer using specific materials. When it comes to houses, this means a massive 3D printer extrudes concrete or other construction materials based on a pre-designed blueprint. Think of squeezing frosting from a piping bag, except instead of frosting, it's concrete, and instead of a cake, it's a fully functional house. These 3D printers are no small feat. They're massive. Imagine a structure the size of a small crane or a garage hangar. For example, Icon, a Texas-based company, uses a system called Vulcan. This printer stands about 11 feet tall and spans over 32 feet in width. Its modular design allows it to expand and adapt to the size of the house being built. The printer operates on rails or special platforms, moving around the construction site. That's why it can print anything from a tiny cottage to a spacious home. Essentially, it's like a large truck, a smart, precise machine that gets the job done with remarkable accuracy. Let me tell you about my visit to one of these construction sites. Icon, based in Texas, invited me to see their house printing process up close. And let me tell you, watching this gigantic printer in action makes you feel like the future is already here. It all begins with architects designing the house on a computer. It's like those 3D renderings you've seen in movies or on designer websites. Depending on the complexity of the design, creating a 3D model can take anywhere from a few hours to several weeks. A simple, single-story house without elaborate details might only take a day or two. But a complex project with unique shapes, energy-efficient features, or intricate interiors? That's a whole different ballgame. Here, architects work closely with engineers to ensure everything checks out. Will the walls hold up under pressure? Are the windows and doors positioned correctly? Are the local climate conditions accounted for? The coolest part? Modern software like AutoCAD, Revit, or SketchUp makes this process faster and allows for detailed visualization of every inch of the house. At the construction site, a massive 3D printer is set up. This printer, essentially a giant robot, moves on rails or with manipulators. It starts printing the house layer by layer. The main material? A special quick-drying concrete that becomes incredibly strong. Once the walls are done, the roof, windows, doors, and other elements are added. At this stage, traditional construction methods are used to finish the house. While the printer can handle the main structure, components like the roof, windows, and doors are typically crafted from traditional materials like wood or metal. For example, the roof might be made of metal or wood, depending on the project. Windows and doors are also custom ordered and installed using conventional construction techniques. This blend of innovative technology and proven materials ensures homes that are not only efficient, but also comfortable to live in. The entire process takes anywhere from a few days to a few weeks, a stark contrast to traditional construction, which can drag on for months. 3D printed homes have a ton of advantages, making them an increasingly popular choice. For starters, they can be built in just a matter of days. These houses are also significantly cheaper than traditional ones. According to Icon, a small home can cost as little as $10,000. And the designs? They're nothing short of art. This technology also minimizes waste and uses eco-friendly materials. Traditional construction often leads to a lot of leftover materials like concrete, wood, and metal, especially when cutting pieces for doors, windows, or walls. But with a 3D printer, materials are used only where needed. The printer lays down each layer precisely according to the design, leaving no excess material behind. It's not just about efficiency, it's about sustainability too. Many companies involved in 3D construction use materials that have a lower environmental impact. For instance, the concrete might include recycled components or be made with eco-friendlier ingredients, reducing pollution during production. Moreover, precise material calculations mean fewer resources are consumed, eliminating the need for extra stock or creating waste that ends up in landfills. This approach not only saves money, but also significantly reduces the environmental footprint of construction. The technology also opens doors to new types of eco-friendly materials, such as biodegradable concrete that incorporates recycled waste or organic substances. These materials reduce CO2 emissions and the need for extracting new resources. So, 3D printing isn't just speeding up construction, it's making it more sustainable and environmentally friendly. It's not just a trend, it's a real shift in the construction industry, one that could greatly improve our ecological outlook for years to come. Of course, it's not all perfect. The technology is still new and comes with its challenges. Currently, most 3D printed homes are made of concrete. But for more complex designs, new materials will need to be developed. These massive printers are also hard to transport and require specific conditions to operate. Plus, many countries don't yet have clear regulations for constructing such homes. Icon can print a house in just 24 hours. One driving factor behind this technology is its potential to address affordable housing shortages. 3D printing dramatically cuts costs on materials and labor. For example, Icon is working on a project to build homes for low-income families at just $4,000 each. The technology also unlocks incredible possibilities for architects. A 3D printer can create intricate, unconventional shapes that are almost impossible with traditional methods. Architects now have the freedom to design without limits, knowing the printer can handle any form or detail. The future of 3D printed homes looks incredibly bright. These technologies are already being used not just for housing, but also for offices, schools, and even hospitals. Icon is building the first fully 3D printed neighborhoods, including a project in the US in 2021 that delivered 5 homes to financially struggling families. And here's what blew my mind. Icon is working with NASA to print homes on Mars. Imagine that. One day, people might live in 3D printed houses not just on Earth, but on other planets too. Icon was founded in 2017 in Austin, Texas, by a group of engineers and entrepreneurs. Their goal was ambitious, yet simple: to create technology that makes housing fast, affordable, and sustainable, especially for those with limited access to traditional homes. The idea came when the founders realized the construction industry was bogged down by outdated methods and high costs for materials and labor. They envisioned 3D printing as a way to simplify the process, lower costs, and provide homes for those in need. Initially, Icon started as a small startup in the construction sector. It quickly gained traction and attracted major investments. Soon, Icon partnered with the Bjarke Ingels Group to create a groundbreaking 3D printed house, marking a significant milestone in the industry. This was the first house printed using technology that reduced material and labor costs. From there, they scaled up to build larger homes for various social programs. In the following years, Icon secured significant funding from venture capital firms, allowing them to improve their technology and expand production. For instance, in 2020, the company raised $35 million, enabling them to grow their operations and launch new projects. Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection. a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/16 to 0.4 of an inch, are suitable for sturdier products like structural elements, or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling, to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end to end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? Lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around, an incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronics stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead acid, can't be recycled together. At smaller collection points, like those in cities, Workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals, For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace, where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials. Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material. stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact, old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning, the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term. A gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. Water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila, a new product appears. the packaging for your favorite smoothie, or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. Ready to explode with curiosity? In this video, we're about to open some top-secret doors to the world of fireworks and firecrackers, things you never even knew existed. Stick around, and you'll see how a simple blend of gunpowder turns into the magic behind the brightest blasts. You'll get the lowdown on the wild history behind their creation and the unusual secrets of master pyrotechnicians. This segment will get your heart pounding faster, trust me. Watch till the end, because the best part is still ahead. Stay with us all the way through, and you'll find out something that'll totally flip your perspective. Don't miss out. Firecrackers, they're the more hot-headed guys in this family. Their main trick? It's all about the sound, not the show. Sure, they're simpler in design, but they deliver the same kind of magic. Noise and pure adrenaline. Like fireworks, firecrackers use black powder as their base, but the approach here is a bit more straightforward. The key is nailing the right balance to get a powerful boom without any extra fancy effects. Typically, a firecracker contains a black powder mixture, a casing, and a fuse. We'll get into what's inside later, but for now, let's talk about the casing. It's usually a paper or cardboard cylinder that holds everything together. The material's gotta be strong enough to hold off the blast till the big moment, but not so tough that it creates dangerous shrapnel. The fuse is the most critical part. It sets off the entire explosive process. It could be a thin cotton wick soaked in chemicals or more modern ignition systems. How are firecrackers made? All the ingredients for the black powder mix are measured out with serious precision, then blended to get the perfect consistency. Accuracy is huge here. Just a little extra saltpeter can make the explosion go wild. Too little, and the firecracker won't ignite at all. Paper or cardboard tubes are cut to the needed length, then carefully loaded with the black powder mixture. These casings typically have sealed ends to build up just the right pressure for the explosion. At the top of the firecracker, a small hole is made for the fuse. The fuse is inserted and held in place with glue or a special sealant. The bottom and top edges of the firecracker are sealed tightly, often using glue or heat bonding. This ensures safe storage and transportation. Next, the firecrackers undergo careful testing. Manufacturers check the sound level, ignition speed, and quality of the explosion. Not all firecrackers are created equal. Cheap ones often have uneven filling, weaker sound, and a bigger risk of misfiring. They use lower quality materials, like plain paper instead of sturdier cardboard. High-quality firecracker casings are made from sturdy yet lightweight material. The black powder mixture inside is evenly distributed for a consistent effect. The fuses have a precise burn time to give you enough seconds to back off to a safe distance. Making firecrackers is no joke. Pyrotechnics plants follow strict safety rules. Workers operate in small crews, wear anti-static clothing, and handle only minimal amounts of mixture at any one time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question comes up a lot. The deal is, a firecracker's explosion isn't just a chemical reaction. It's a massive release of energy in a confined space. When the powder burns, it releases hot gases that expand super fast, creating a powerful shockwave. And since the casing is tightly packed, that wave comes with the trademark boom sound we all know. The word firecracker comes from the French pétard, meaning a blast. Like fireworks, firecrackers trace their roots back to China. Initially, they were used to scare off evil spirits, and only later did they become a popular form of entertainment. Today, firecrackers are an essential part of many celebrations and festivals around the globe. But their history shows that even the simplest things can have deep roots and a fascinating evolution. So, the next time you hear that familiar bang, remember just how much skill, history, and technique is packed into each tiny firecracker. When it comes to making fireworks, you also start by mixing gunpowder with other components. If you think of gunpowder as the engine of the firework, then the other materials are the artists who create that explosion of color, light, and shape. To get bright sparks, you need metal powders like aluminum, magnesium, and titanium shavings. For vivid colors, you rely on metal salts such as strontium, barium, copper, and sodium. To boost the energy of the blast, you add ingredients like potassium nitrate, perchlorates, and charcoal. These act as oxidizers and fuels. And to hold it all together, you use binding agents, like water-soluble glues. Each component is first ground into the finest possible powder. Picture shining metal particles dancing in the light as the master prepares them for blending. These powders are so lightweight, it's almost as if they're suspended in midair, like some kind of magical dust. The most important step starts when the ingredients go into a mill filled with ceramic or wooden balls. These balls rotate gently, grinding the mix into a perfectly uniform blend. There's a soft rustle and a light tapping sound, kind of a subtle rhythm, reminding you that a future burst of colors is being born. As for mixing the ingredients by hand, at traditional production sites, this step is done with great care and reverence. Specialists slowly and carefully blend the ingredients with wooden or copper paddles. Why so slow? Because even a single stray spark could set the whole thing off. The mixture looks like a shimmering sand, where each component has its role to play. To avoid accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds a sort of mysterious alchemy. as gunpowder and colorants form tiny granules. The smallest mistake can cause a tragedy. You know what pyrotechnic masters do before they start working? They remove all metal objects, even wedding rings, to prevent sparks. In many labs, cell phones are strictly forbidden, and employees wear anti-static clothing. Even the air matters. Conditions are kept humid enough so that mixes don't dry out and become dangerously volatile. Before packing the mixture into the casing, the masters test how it burns. A small sample is ignited, and everyone holds their breath. Is that the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors. That's the coolest part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged. These are tiny pellets with a special composition. Where'd those brilliant reds, greens, and blues come from? All thanks to chemical compounds. For instance, barium makes green, strontium makes red, and copper makes blue. Once all the components are prepped, the next crucial step is filling the casing, where the heart of the future firework is born. It's right here that the explosive mix and colorants become a finished product, capable of painting the night sky in every color of the rainbow. The casing is a shell that holds all the fireworks parts together. It's made from special materials that can handle high pressure and heat, yet remain light enough to shoot into the sky. Cylindrical shapes are perfect for forming sharp patterns like rings, chrysanthemums, or peonies, while spherical shells create symmetrical three-dimensional effects, like a glowing orb exploding into hundreds of sparks. The filling process is super important, because the exact placement of components ensures the desired effect. Let's break it down step by step. First, you take cylindrical or spherical shells, usually made of cardboard, plastic, or specially treated paper with fire-resistant properties. Spheres typically come in two halves that will be joined later. It's crucial that the casing is airtight. That guarantees the explosion happens at the right moment with the right intensity. The black powder charge, acting as the main engine, sits at the center. It's responsible for propelling the firework skyward and making sure it explodes properly. Around that charge, the colorants and special effect mixtures are arranged. Each tiny star element is placed by hand or using special machines. These stars are what we call the pellets that burn in the sky. For spherical shells, these stars are placed evenly, so that when it explodes, it forms a perfect sphere of light. In cylindrical shells, charges are often laid in layers or formed into specific patterns, depending on the planned effect. One standard spherical firework can hold about 200 to 300 pellets. Large, multi-layer shells might have over 1,000 of them. To ensure the firework explodes at the right time, a time delay fuse is added, a small tube filled with a slower burning composition. This timer connects to the main charge, providing a delay between the rocket's launch and the burst in the sky. After all elements are in place, they're secured with a special paste or paper spacers. This keeps every component locked in position during the launch. The casing might then be wound tightly with string or glued for extra rigidity. Crafting one large professional-grade firework can take up to 4 hours, considering all the careful assembly and testing. For a massive show with several thousand shells, pyrotechnicians might work for a few months straight. The spherical shape is the classic standard in pyrotechnics, giving an even spread of stars and creating that perfect circular effect. Filling such a shell requires even more skill. Each star is placed by hand around the central charge. It's all on the master's shoulders. How the components are arranged will define how the explosion looks. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the powder ignites, those pellets spread out just right, forming the intended pattern. Every year, over 200,000 short tons of fireworks are produced worldwide. China is the leader here, accounting for about 90% of the global output. For major holidays, like Independence Day in the United States or New Year's Eve in Sydney, up to 10,000 separate fireworks might be launched in a single night. Such a display can last over 20 minutes and sometimes costs as much as $5 million. Despite the beauty of fireworks, safety stats are pretty alarming. In the United States each year, up to 10,000 injuries are reported due to improper use of pyrotechnics, with about 70% of the injured being young people under 20 years old. You wouldn't believe how much technology goes into making ordinary toilet paper. Robots cutting trees with laser precision, machines rolling them out at speeds of hundreds of miles per hour, and even artificial intelligence monitoring every single inch for quality. After this video, you'll never look at toilet paper the same way again. Watch till the end. It's going to blow your mind. Let's dive right in. The process starts at logging sites, where machines known as harvesters are used. These impressive machines cut down trees, strip them of branches, and chop them into logs of precise lengths, all in one go. Honestly, I could use something this multifunctional for cleaning my house. Logging is meticulously planned, using GPS and GIS to identify optimal areas for cutting while adhering to strict environmental standards. Trees are harvested selectively to prevent over-deforestation. Logs are then transported to pulp mills by specialized trucks equipped with GPS trackers that optimize delivery routes. Alongside fresh wood, these factories also use recycled paper, collected through recycling programs, delivered as compacted bales. At the mills, the logs are fed into automated lines, where they're chipped into small, uniform pieces. See how tiny these chips are? That's thanks to industrial-grade chipping machines, equipped with sensors to control wood size. These chips are moved along automated conveyors to massive digesters. Before entering the digester, the chips pass through magnetic separators to remove any metal and sieves that ensure uniform size. Sensors and computer systems manage every stage. Inside the digester, the chips are mixed with chemical solutions like caustic soda and sulfides, a process called the Kraft method. Automated dispensers precisely measure and add chemicals based on the type of wood being processed. Feeling the heat yet? Inside the digester, the chips are heated under high pressure for several hours. This entire process is automated. Computer systems carefully control temperature, pressure, and cooking time to produce the perfect consistency of pulp, a mixture of solid particles and liquid. Now, check this out. The pulp is pumped into centrifuges, which remove heavy impurities like stones, sand, or metal. Chemicals are then added to break down any remaining linin, the substance that binds wood cells together. Advanced sensors monitor temperature, pressure, and chemical concentrations to achieve optimal pulp brightness without wasting reagents. After this, the pulp is washed to remove residual chemicals and byproducts. Multi-stage washing systems clean and recycle water, minimizing waste. Oh, you're still here? Great. Quick story. One Halloween, I was completely swamped with deadlines. Instead of competing in our neighborhood's annual Best Holiday Decorations contest, I gave up. In a moment of pure laziness, I TP'd my own house, just like in those classic prankster movies. Surprisingly, it got more compliments than any decor I'd ever done. The irony, right? Anyway, back to business. Once purified and bleached, the pulp, which now has a creamy consistency, is piped to forming machines. Sensors installed in these pipes monitor temperature, moisture levels, and pulp density. The pulp is spread onto a forming table, the core component of the paper-making machine. This section consists of an endless wire mesh, moving at speeds of up to 63 miles per hour. The pulp is evenly distributed onto the mesh through nozzles, and excess water is removed immediately using vacuum pumps. The sheet then moves to the press section, where special rollers covered with silicone or rubber squeeze out more moisture. Next up, drying. The sheet passes through a giant cylinder known as the Yankee dryer, heated to temperatures between 240 and 300 degrees Fahrenheit. By the end of this stage, the paper's moisture level drops to around 5%. Sensors constantly monitor the cylinder's temperature and rotation speed to prevent overheating or overdrying. Now for the finishing touches. The dried sheet undergoes embossing, where textured patterns are pressed onto its surface. This step enhances the paper's softness, absorbency, and appearance. Steel or rubber rollers with intricate designs create these patterns. Automated systems ensure the patterns are crisp and evenly applied. Some manufacturers add fragrances or moisturizing agents at this stage, spraying them on in thin layers using advanced nozzles. Optical and ultrasonic scanners monitor parameters like thickness, density, and uniformity. If defects such as tears or uneven textures are detected, the system automatically adjusts or discards the flawed section. Data from all scanners is fed into a central computer, analyzing the entire line's performance in real time. It can even predict potential issues, like roller wear, and notify operators for maintenance. Cool, right? After forming and drying, the paper is rolled into massive jumbo rolls. These rolls can measure several feet wide and weigh hundreds of pounds. Robotic arms transport the jumbo rolls to the rewinding section, where the sheet is unrolled, smoothed, and prepped for cutting. Rewinding machines stretch the paper and roll it onto cardboard cores, which are automatically fed into the line. Check this out. These machines can wind hundreds of rolls per minute, and they're constantly monitored for tension or defects. If something's off, the system pauses to prevent waste. Once rewound, the rolls move to the cutting section. Here, larger rolls are sliced into smaller, standard-sized rolls using high-speed cutting machines. Titanium or steel-coated blades ensure clean, precise cuts without damaging the paper. These machines operate with millimeter precision, guaranteeing uniformity. Automated systems monitor blade sharpness, replacing dull blades without interrupting the process. Each roll undergoes final inspections via high-resolution cameras and infrared sensors, checking diameter, density, and cut quality. Defective rolls are swiftly removed using pneumatic arms. Finally, the finished rolls head to the packaging section. Robotic systems handle them without contact, reducing contamination risks. Sensors align the rolls before they enter the wrapping machine, while a computer system ensures all rolls meet size and weight standards. The rolls are grouped into packs, 4, 6, 12, or even 24, based on consumer demand. Robotic arms stack and wrap the rolls using either thin but durable plastic film or eco-friendly paper packaging. This ensures protection from moisture and dirt while catering to environmentally conscious buyers. Behind every Casio watch lies a story that not many people know. Today, you will discover the truth about Tadao Casio, the visionary behind one of the world's most renowned technology brands. From revolutionizing the industry with the first digital watch, to the controversial associations with Al-Qaeda, stemming from the use of Casio watches in terrorist bombings, Casio has left an undeniable mark on history. In the quiet village of Kuretamura in Kochi Prefecture, on November 26, 1917, a boy named Tadao Casio was born. His arrival into the world coincided with a time of great upheaval and change in Japan. From an early age, Tadao's life was shaped by a series of events that not only tested his resilience, but also molded him into one of the country's future technological pioneers. In 1923, when Tadao was just 6 years old, the Great Kanto earthquake devastated Tokyo and Yokohama. This natural disaster forced the Casio family to leave their home in Shikoku and relocate to Tokyo. At the age of 14, young Tadao began working as an apprentice lathe operator to support his family. This early experience sparked his interest in mechanics and innovation. Simultaneously, he continued his education at Waseda Workers' School, excelling academically and graduating from both junior and senior schools in 1923 and 1930, respectively. Tadao's school years in Tokyo were challenging, but he adapted, demonstrating the resilience that would later define him. During this period, the Casio family grew with the arrival of new members who would later play pivotal roles in the brand's history. In 1925, Toshio Casio was born in Kyobashiku, Tokyo, followed by Kazuo Casio in 1929. These brothers, along with Tadao, would eventually join forces to establish one of Japan's most influential technology companies, Casio Computer Company. During the 1930s and 1940s, the world was plunged into the chaos of World War II. Among those affected was Tadao Casio, a young man with a vision that transcended his time and circumstances. Due to health issues, Tadao was unable to serve in the military. However, he contributed to the war effort by manufacturing aviation parts in a workshop attached to the family home. This work was not only a form of service, but also an invaluable lesson in precision and mechanics, skills that would prove crucial in Tadao's future entrepreneurial ventures. In 1942, Toshio Casio graduated from the School of Electrical Engineering, now known as the Tokyo University of Electrocommunications, and joined the Ministry of Communications, where he specialized in research on Morse code transmission. 1943 marked a pivotal year for Tadao Casio. He married Shigi Noguchi. Together, they endured the hardships of war and the challenges of the post-war era, raising 3 daughters and a son in a country rebuilding from devastation. The end of the war did not bring immediate relief. American bombings had destroyed the Casio family's home, halting their manufacturing operations. However, this adversity became a catalyst for Tadao to rethink his future. A symbol of this fresh start was the purchase of a milling machine, which Tadao transported over 200 miles. This machine not only enabled the family to restart their business under the new name Casio Manufacturing, but also became a testament to their entrepreneurial spirit. In 1946, as post-war Japan embarked on a path to recovery, Tadao Casio, along with his father Shigeru and brother Toshio, founded Casio Seisakusho in Mitaka, Tokyo. Their first invention was the Yubiwa pipe, a cigarette holder that allowed users to smoke a cigarette down to the very end without burning their fingers. This simple yet innovative product marked the company's first technological breakthrough. In 1949, a pivotal moment occurred. Toshio saw several imported calculators at the first trade exhibition in Ginza, Tokyo, which inspired the Casio brothers to reinvest their profits into developing their own calculators. By the early 1950s, all 4 Casio brothers were actively involved in the family business. Tadao managed administrative matters, Toshio led research and development, Kazuo was responsible for marketing and sales, and the youngest brother, Yukio, handled production. In 1954, the Casio brothers completed the creation of Japan's first electromechanical calculator. This device featured a 10-key numeric keypad, marking a true breakthrough in calculator design. In 1955, the brothers showcased their revolutionary solenoid-based calculator technology at the Bunchoro Corporation in Tokyo. This innovation made calculators quieter and more efficient, symbolizing a departure from the bulky, noisy designs of the past. However, in 1957, a serious incident occurred. During a demonstration of their calculator in Sapporo, the device had to be disassembled for air transportation, but ended up breaking. As a result, the brothers decided to abandon solenoids and transition to using relays instead. Relays are electrical switches that allow a low-voltage circuit to control a high-voltage circuit without direct contact between them. This change significantly simplified mass production. In June 1957, the company adopted a new name, Casio Computer Company. They launched the Model 14A, the first fully electric compact calculator. This marked a significant milestone in the development of consumer electronics. Operations that previously took around 10 seconds on other devices could now be completed in just 5 or 6 seconds. Additionally, the model featured only 10 numeric keys, serving as a prototype for modern calculators. In 1960, Tadao Casio became the president of the company, succeeding his father, Shigeru. This marked the beginning of a new chapter in the company's history. Casio began exploring new technologies and became a pioneer in manufacturing quartz watches, both digital and analog. In 1965, the company initiated mass production of desktop calculators. By 1967, they had opened an office in Zurich to serve the European market, and later that same year expanded into the United States and Canadian markets. Quite remarkable persistence, wouldn't you agree? A major breakthrough came with the release of the Casio Mini in 1972. This was the first personal calculator model affordable for the average consumer. Within 10 months, 1 million units were sold. In 1974, the company introduced the Casiotron, one of the world's first quartz digital watches, with an automatic calendar that accounted for months and leap years. During the 1980s, the company ventured into the music industry, launching electronic keyboard instruments such as the Casiotone 201, which revolutionized the music world. In 1983, the world was introduced to the G-Shock, a durable and long-lasting watch that became a global phenomenon. It was designed by Casio engineer Kikuo Ibe, with the goal of creating an unbreakable watch. The concept of the G-Shock was based on 3 key principles: the ability to withstand a fall from 10 meters, water resistance up to 10 bars, and a 10-year battery life. To this day, G-Shock watches remain the most popular product in Casio's lineup. Athletes, especially divers, swimmers, and climbers, rely on these watches. They endure low temperatures, feature scratch-resistant mineral glass, display moon phases and tidal patterns, synchronize time via radio signals, and operate flawlessly for 5 to 10 years. Additional features include a stopwatch, alarm, timer, backlight, and date display. More than 200 prototypes were developed before the DW5000C model was launched in April 1983. The watch quickly earned a reputation as the toughest in the world. The G-Shock also offered digital watch functions such as a stopwatch, countdown timer, alarm, backlight, and the option to toggle between 12-hour and 24-hour formats. In 1989, Casio released the iconic F91W watch, which became one of the most affordable digital watches in the world. It cost less than $20. The watch featured functions such as a stopwatch, an alarm signal, an automatic calendar, and a backlight. Its battery lasted up to 7 years, and it boasted an accuracy of about 30 seconds per month. However, the F91W also became a subject of controversy. In the 1990s, it was associated with use in terrorist devices due to its durability and affordability. As is often the case, when someone creates a device to improve lives, others find a way to use it against human life. After nearly 3 decades at the helm of the company, Tadao Casio passed leadership to his brother, Toshio. However, he remained an advisor and shared his expertise through various publications. The company continued to grow even after Tadao's passing in 1993, leaving behind a legacy of innovation and accessibility.